I'm David Holland, Technical Director from Salix. I'm going to talk more generally about river processes and working with natural processes and using wood in particular, and the combination of using the whole trees and wood within revetments and using site-one materials in order to sort of provide sustainable bank revetments. Rich covered it a bit, but because I just done this presentation late last night, I'm going to keep my slides in as well. We've covered a little bit of the same ground, but just to put it into context. So traditionally, how we managed our rivers? Well, in the 50s and 60s, land drainage, we messed our rivers quite a lot. The will to get water made to be as quickly as possible. Can you see a river there? You see a river there? No. That's the river. So obviously we straightened our rivers, we managed them, man rule, nature type of Victorian legacy type approach. And a lot of our rivers we've messed up quite badly. This is always quite an interesting scheme, just like Carmarthen. And years ago I used to go down and look at it, and every year another 20 metres of blockstone being built, and the erosion downstream got worse and worse and worse. So I think it's generally acknowledged now that sort of hard engineering, particularly in the context of the Water Framework Directive, isn't great, and there are more sustainable ways of managing our rivers and our river banks. What does hard engineering do? The biggest impact is directly on the riverbanks. A lot of invertebrates and creepy crawlies need to come out of the river, climb up onto vegetation, so it cuts off the whole riparian and aquatic life cycle of a lot of creatures. In America there's been studies to show too much rock actually increases water temperature, which isn't good for fish. It's a physical barrier for mammals, for burrowing. It passes, it creates turbulent flow, and it passes accelerated flows downstream. So often, very commonly associated with hard engineering is downstream problems of instability, riverbed, bank, incision, those sorts of things. In terms of effect on habitats, one year we reckon that 30% of our turnover was down to the waterwall. Mitigation works, mainly in southern England. Obviously all the key statutory protected species are affected by over-engineering rivers and straightening and hard engineering. A really good example is on St Asaph on the River Elbe in North Wales. You can see quite a big pool feature here, bank erosion. The main high pressure gas pipeline through the whole area runs underneath there, and underneath there is actually a 4.5 metre deep pool, which is scoured out at the bottom of, you can just about see this run here, of gabions, which were put in originally to try and protect the pipeline. All they've done though is cause this accelerated flow around the outer bend, and a huge scour hole has formed here, actually exposing the pipe on the bed. So that's a bit of a hotspot. We did some 2D modelling on this, and this is looking downstream, so this is the gabion baskets. So as you come downstream, at the end of the gabion baskets, you get this hotspot and this pool forming. So all the energy is effectively transferred downstream. There's a close-up of that hotspot. You can see off the nib, the corner of the gabion baskets, you get this real high energy, high shear on the bed, hence all this scour of the bed material. So our solution to Wales and West Utilities, who are the pipeline owner, is effectively to de-engineer the riverbank, or de-engineer the river, and give it far more capacity. So what we've done is actually taken out 4 metres of gabions, graded the banks back. We've used our rock mattresses in the toe here, and we've actually reused some of the original riprap which was in front of the gabions and buried into the bed as toe protection. So far more natural bank profile. And what that is effectively, when you run the model again, that hotspot is now gone, because when the flow comes around it's slowed massively, so a lot more area, a lot more room, a lot more friction and roughness on the bank, so you don't get this hotspot, and that pool is actually filling in naturally now. So just by working with natural processes, we've solved that problem without having to import. I think we put 200 tonne of stone to cover the pipe, but we would have been importing thousands of tons to fill a huge 20 metre by 40 metre by 4 metre deep pool. There would have been a lot of stone to fill that. So over time now that's natural. So this is what we mean by sort of working with natural processes. There's also been a general movement away, Rich sort of alluded to it, from hard to soft engineering. This is in Pembroke Commons, the old culverted channel, part of the FAS scheme there. They broke out and we meandered the new sort of river restored channel. And a lot of our work early days, sort of 17, 18 years ago, were on very much lowland rivers. The confidence wasn't there and the experience and knowledge wasn't there to soft engineering, bioengineering into higher energy environments. So this was sort of a classic sort of mid-2000 scheme where biodegradable blankets, coir rolls, marginal planting. If you've ever been to Pembroke on the Commons, it's a beautiful little stream now, very natural looking, from that sort of culverted, open culvert channel previously. And a lot of that, again, more recently has been probably water framework directed led. Then for this scheme it was probably more aesthetics and landscape value. Now it's probably more WFD. So Rich defined bioengineering. It's anything that involves vegetation, often with natural fibres or often with man-made synthetic fibres or in combination with rock. So it covers a broad range of solutions. Again, Richard, all the same slides as me.
Mine's slightly different. The size of the country, that's why we need to talk. You're better than me, just go. So
bioengineering ultimately relies on plants. So you've got to have a sort of basic knowledge of plants, where they grow on the river bank, how to establish them. Is it seeds, is it cuttings, is it plants, is it in live sort of coir roll systems, where those sort of establishment techniques are appropriate. Rich again mentioned about some of the products that have been tested in America, these reinforced grass. There's also been a lot of work done on willow revetments, so spiling, brushwood revetments in the alpine areas. So this is Austria, downstream of a reservoir. They've sheet-piled this huge halfway through the channel to create this flume. They then established 4 or 5 different willow techniques and different bank angles at different age life cycles, so 6 months old, 1 year old, 2 year old, and they let controlled flows through there. So we've actually got some really good knowledge about what sort of revetment, organic revetments can withstand in terms of flows from the day they're installed right through to 3 or 4 years on, which is great. Obviously, having worked out for however many years, 17 years, we've also got some really good examples from the UK of rivers. Rich showed the River Ebu, which was one of our very early jobs in 2004. This has now obviously had a lot of virtual bankful events. We know the shear stress that goes through there, we know the flow velocities. This is it not long after establishment, 1 year after establishment. So with this now we can actually say, well, we know, the stream power here was X, or the shear stress on the bank was X. We know this system can withstand those sorts of flows, so we can transfer that and give confidence really that these techniques will work. Why is the vegetation element so important? Effectively, if you're putting an revetment on, you're covering up soils. Soils are a natural living ecosystem. You can't remake a natural soil, it takes hundreds of years to form. So by putting vegetation on there, you're preserving it without effectively covering it. It improves infiltration, you get the physical habitat obviously that you associate with invertebrates and mammals, but it also slows down locally water flow velocities. So it actually can actually slow, adds roughness to the channel bank. It self-repairs obviously and evolves with time. And we've done a couple of schemes up in Aberdeen where we actually showed that by having settlement areas of vegetation off the river, you can actually greatly improve water quality as well. So you can take out a lot of suspended solids and nasties as part of river restoration. So, nice to see Anne here, your resident geomorphologist. So it's everything we do is all about working with natural processes. And the first thing we always do is identify what's causing erosion or what's likely to cause erosion in the future. So here you've got a classic sort of low gravel bed streams, the Collie in Devon, Iron and Aber-Iron, where you've got this sort of classic undercutting. Often you have a gravel layer in here that gets exposed, take it away. The bank steepens. undercutting, bank steepens, and you get slab failure. Classically called a cantilever type failure. Probably the most common form of erosion in Welsh rivers. You can see on this job of the iron here, there's a big tree here which is deflecting the flow in here. So this is a really simple, it's a public footpath on the top. So rather than move the footpath, it was a case of not stopping the erosion, but managing the rate of erosion. So this is the main theme of this presentation, is try and work with materials on site to actually create your revetment, solve your own problem. So we've taken the tree out. We've actually driven in big large stakes all the way along, 2 rows, and then we've packed all the branches, logs and trees as big units in there, and we've planted willow cuttings in behind, but we just left the bank steep, we left the bank naturally steep. We've removed the problem, we've basically packed out the toe area where all the process was happening, so if you leave that now, over time it will naturally stabilise. And that's about 3 years on, effectively you've got a slightly shallower angle, it's slowly over time just naturally eroded back to a natural angle of repose. Because you've dealt with the cause, then longer term that's a stable, I think that was a day's work for 30 metres of riverbank. Really low tech, cheap a way of doing that sort of river work. Quite a lowland river, not particularly high energy, but obviously it's the iron, it gets quite a flow through it in terms of volume. Another quite common erosion process. You have to look very carefully, is this going to be too dark? No. So this is the River Team in Broadwas, just on the Hereford-Wales border. Very, very flashy, so this came up in about 4 hours. 5 metre vertical rise in the river while we were working. If you look here, just here initially, as the water starts to recede, you get the drawdown. So you just see the bank starting to go, moving, and the crack forming all the way along the top here. And the whole erosion mechanism is different to the last example. So here, if you put something at the toe, it would have no impact. It's the drawdown effect and the build-up of pore water pressure within the soil that just creates those slabs of soil to pop out. So the solution here would be to either drain the bank back, somehow reinforce it, or physically retain it with some sort of retaining structure. And it's best in all these areas with high pore water pressures to actually create the bank if you've got the room. So a good example of that is the Mono at Kenchurch, and if you didn't know this scheme, it was a weir removal. The weir is removed effectively, the channel bed incised, got the gravel washed straight through, and then the bank erosion resulted. And again, these sort of red, sort of sandy sandstone soils you get around the Mono catchment. So the water comes down, the whole bank just slops out. It's got no strength in it whatsoever. The main reason that MLW did this work was effectively to control fine sediment inputs into the stream, into the river system. So again, low tech. We're not looking at stopping erosion, we're looking at managing the rate of erosion. The only imported materials we brought in was some coir matting. Everything else was actually harvested on site. So the bank's graded. What's up far along? Somebody losing the will behind me. So yeah, graded the banks to a natural angle of repose, seeded it, put some erosion blanket and erosion netting on them. The combination works pretty well. If you don't want to use plastic, that's the highest performing natural materials you can use. And then at the toe, to protect the toe, we've put in, from the far bank, we've actually harvested whole trees and staked and laid them around the whole bend. It's about 230 metres of bank. There's been a few of these washouts, but again, it's not small pockets of erosion, but you see the rate of erosion is the objective's been reached, the rate of erosion is reduced massively. And in terms of habitat, you've got all this overhanging vegetation, you've got all these fisheries habitat in here. This will continue to grow up and provide good cover for fish as well. Okay, a good example again of working with natural processes using soft engineering. This is up in Rainton in the north of England. So it's a northern gas pipeline. We do a lot of utilities companies' works. So we were tasked with coming up with a solution, and the client's first idea was just to put blocks all the way along and over and protect that way. So this is the original current line that we're looking at here. pipe is just exposed here. But what you've got effectively, this is flowing upstream to downstream. What you've effectively got is this really tight radius. So it's like a dog leg, 90 degrees. And what that was doing was backing up the flow, and all the cobble and gravel was dropping out in the middle, creating a huge bar feature which was pushing the flow there. So we said, well, it's pointless just protecting this here, because this bar feature will continue to grow and eventually probably undercut anything we've got there. So the solution was actually to move the channel back to one of his historic channel routes. So that was the original route through here. We diverted it here just temporarily, and then left that as a backwater, and this is the new route. So effectively what we've done is we've increased the channel length. We've modelled it to show that we won't get problems with future deposition. We actually want the cobble and gravel to move through sweetly on that bend. You'll see from the last photo that we've got really good sediment transport now, where the old channel here has been filled in, but that now could flow right around this tight bend, and so you basically don't get the huge bar features forming that are deflecting the flows everywhere, causing erosion. So again, it's removing the cause really to have a final impact, and that's it. That's been about 4 years on, so you've got this sort of backwater feature. The gravel's nice and clean, the sediment can transport through the system nicely. And again, when we modelled it, when the original channel was straighter, we couldn't get bioengineering to work. The energy levels are too high for coil rolls, but by increasing the channel length round, we actually could use them software engineering techniques. When we've literally just finished last week, a Wales and West pipe. The landowner reported this 4 years ago originally, and it was just showing a little bit here. Since then, over this winter, it's gone back about 4 or 5 metres. So that's this point bar feature. And again, it's very similar to that rate and burn scheme where you've got the original channel that flowed down this side, then you've got probably a tree come out at some stage in here. This is very predominant channel forming process is trees falling in and then creating erosion and scour and gravel bars forming. They've left it for a year, obviously. The pipe was only a little bit exposed then. A year later, it's exposed for about 4 or 5 metres, literally suspended in water, which is quite a scary thought. You can see that the evolution of this gravel and cobble bar here has grown in height and extent. It's joined up to this bit of wood in here. So that's that dog leg. Again, the dog leg is creating a backup effect, so you're getting all your cobble and gravel dropping out. So the solution here is actually to, and it's not a project we designed initially, it was Halpro designed it, NRW consented obviously, but the idea is to remove the channel back to its original course before the tree would fall out. That's where it sort of flowed 4 or 5 years ago. I don't know whether this will play, but some video from last week. But what we were really concerned about from the original design, which was just rock groggles on the new channel edge, is that the whole thing would get undercut. So in this sort of rivet type, the best thing to stop that sort of undercutting is to use large wood. And by Jove, the weekend we were working, it was quite windy, and an alder fell in upstream. The lady in the house behind actually heard it go. So we've reused this alder, cut it into 3 sections. This has just been placed. Eventually the whole thing will be sunk below bed level. So that if that channel level wants to go back that way, which it always will want to now probably, it's going to hit effectively 4 or 5 tonnes of log over that 20 metres. That's the final bank profile. So again, we've actually come out to about 5 or 6 metres here. The original design had some deflectors in to try and build up gravel on this side of the bank. So effectively we're swapping process, we're switching the process from left to right. The large wood, there's lots of ways of anchoring them. The one we've used a little bit, but not a huge amount, is with these ground anchors, platypus anchors. You drive them into the gravel bed or bank, and then you tension them, and the anchor flips round, creates a surface area of resistance. So you can actually calculate flow and drag and buoyancy, and then you can actually calculate the size of the cable and the anchors that you need to stop that from being entrained. So in terms of flood risk, you can pretty much design that out. Pinning is a very common way with pegs or metal. The best way of all those is to actually embed it within the bed and bank. So here we're placing just a big trench here. So we're actually placing a huge oak log up on a job in North Yorkshire as a deflector and that is purely being anchored by the weight of the gravel. Yeah, so anchoring these things, there's numerous ways of doing it, but if you can get it half in the bed and bank, that's normally the longest term solution, is to fix these bits of wood without relying on stakes or bits of wire, which eventually will degrade and disappear. But I mean, these anchors have got 120-year design life on them, they're stainless steel. If you can get it in the bed and bank, well, that's better. We do quite an innovative one for you guys up at Clun Park, slowing the flow around the valley. It's an old colliery site with land drainage scheme, effectively blockstone to move water away. So there we've actually just anchored into blockstone. So all the wood features there are there to slow the flow and try and get it to overtop rather than rushing down. So that we've anchored in using 12mm stainless steel. Some of these are weighing nearly a tonne in weight, so it's quite a weight to hold down, but it seems to be working fine. Again. So I was going to focus on one scheme we did in 2012-13. Again, another high pressure gas pipeline. And the reason I'm going to use this as an example is we used about 5 or 6 different techniques using wood. All the wood was harvested from within 2 or 3 catchments locally. And that's our biggest issue doing this sort of work, designing this sort of work, is sourcing materials. So we're hopeful with your nicely integrated forestry and rivers and coastal teams, you'll be able to help us with that. So the Roo is effectively a catchment of the Severn. Here's the Severn, the Roo flows in, and again you get quite a lag on the Severn rising and falling compared to the Roo. So you often get, when this is down, the Severn is up, so you get a lot of backup of water, so you get a lot of deposition in here. So you get a lot of active movement. It was traditionally been overgrazed. The area where the gas pipe was exposed was just on this nip here. It was actually for 26 metres dangling in thin air. If that goes bang, it's quite a big bang. So the area we're looking at here is opposite. The pipe actually comes through. So we're protecting this bank initially. And again, you know, the client's first instinct is always just to go for something hard, because it's effectively the main high gas pressure pipeline through mid Wales. But we thought, well, no, you know, the hard had been tried here before. The original channel line was actually, when this pipe was put in, was effectively blockstone right through the middle here, and it's just jumped out of that channel within a decade and moved around so much. So the whole idea of what we're trying to do is slow the flow. Stop the gravel becoming so mobile, and get roughness on the banks through getting vegetation and trees on them. So on that little bend there, we've got a big bar formed, pushing the flow in there. This tree was about to fall in, literally completely undercut. So rather than allowing nature to do it, we felled it. And we've used that as the bank revetment. So we just sat on this little point bar here, and we're placing in. And with wood, generally the bigger the better. We use a lot of brash on the surface here. The bigger it is, the more chance it's got of staying, and the bigger impact it has. And then we're just using a sort of whole network of chestnut and large posts driven in, all wired across, to hold the whole thing down. And then we've actually then used some gravels from that bar just to backfill over that, to try and hold it all down. And because it was willow, you know, that same year it all starts to grow, and that's, I think, about 6 foot tall now. Great on a big river like this, but no good on a little stream, as Richard said. There'd be a flood risk and a maintenance issue. But here, the only trees that tend to grow are alder and willow, so it's natural. Upstream, there is one very naughty little tree. This is in here, and every time the tree moved, each flood, it would create a huge tail of gravel, which would deflect flow across into the bank. And they actually lost 8 metres of bank in one flood event, pretty much, or 2 major flood events over a 3-month period. So this was obviously upstream. The pipe runs diagonally across this field, so it wouldn't be long before it got all the way back into the pipe again. So rather than do a sticky plaster, they whereas the west side to look at the whole reach. So what we sourced was over 50 of these tree roots, Americans call them root wads. Getting very, very good revetment for outer bends of rivers. So what we've actually done is dug the riverbank away, put a bit of a rock roll towing. On some areas where we could get enough material, we put whole oak logs, sort of 400, 500 diameter, big oak logs. And that's again just to prevent the all undercutting. And we've backfilled over them to create effectively a really rough face. A lot of them were willow, and we're planted with willow and alder. So that's it, not long after construction, that's at the end of the first year, pretty dark. You can see now that's a really well vegetated, stable bank. And certainly the gravel bar opposite has settled down a lot, it's not jumping around, it's not moving. And that's all because of the roughness now we've applied to that bank. You imagine more river and flood through here, it's got absolutely no roughness here, it's just moving through really, really quickly. Now you've got a really rough graded bank with all that sort of woody material slowing the flow down, and obviously perfect fish habitat. Now you've got little scour pools underneath each of those root wads, very local, so it's a good fish habitat. That's the one bit of troublesome wood, it's jumping around everywhere, as is my presentation. So you can see it's a fair chunk of wood, it's originally a very big root plate, I'm not sure what tree it was, but we took it out because it was deflecting the flows across, and we decided to reuse it. About 80 metres upstream of the pipe, where the pipe was originally exposed, because what we wanted to do is recreate this natural tail you get. So you can see this is where it came from. That's it. 18 months later, going in. 18 months later, you can see all the banks are well vegetated. You can see how much vegetation is established. This we all fence to keep the cattle and sheep off. That's really important. Then you can see then the start of this tail of gravel. So you tend to get a little bit of scour here, and then you get this gravel build up, and it's quite remarkable. The original bit of wood went in there after one flood event. That's the gravel deposition downstream. Here's the exposed pipe. This is where the pipe was exposed, directly across here. So the client wanted to put that bit of blockstone in, belt and braces, but that bed load response is a really useful tool to be able to get the bed from incising and cutting down and undercutting that whole corner again. So as long as that bit of wood stays there, then that gravel bar will stay there effectively. So again, just working with natural processes. In terms of longevity, that's what we always get asked on these sorts of schemes, is how long would something like that last for. We did a demonstration project on the Dull Ice in 2003-04, I think, our first year when we started. It was all very innovative and new, and we didn't really know a lot what we were doing. It was all trial and error, and Environment Wales and Ben Wilson back then were really good to give a bit of confidence in us that we knew a little bit about what we were doing. So it was a demonstration to show that big wood could be used effectively instead of blockstone on Welsh rivers. We came up with a scheme that's now basically picked up by the River Restoration Centre. It's in E8 design guidance and SEPA's design guidance, using these root wads. So again, you've got this classic sort of cantilever failure where the toe gets scoured and the bank steepens up. All we've done is put these root wad revetments in, anchored them no other way than just a trench back in the bank, graded the bank back, and planted above it. Okay, we were quite lucky here in that we had an adjacent forestry, private forestry, that wanted to get rid of all their willow, all their marginal stuff that was competing with the crops. So we had 20 or 30 root wads brought in. You can't really see it, but there's a trench that goes back in here. So the whole of this stump goes back in, and then all you're left with is a root plate on the surface. I see it a bit better here. So you can see each of these root plates along the riverbank there. Again, if you look, there's a slight gravel bar forming here. Because we've slowed the flow down substantially, that bar is growing, actually protecting this bank. You've got all the growth, all the willows starting to grow, and you've got the whole thing is settling down, the whole reach. So if you've got sort of reed canary grass and other grasses coming in naturally, which also helps stabilise. And that was, I think, 10 years on. So again, it's still there, it's still working. And that's where the original root was. It's quite amazing because they're willow, effectively, that's the original root. The willow's got the ability to regenerate and send up new growth off the plate of the root, the top of the root. And you can imagine in terms of fisheries habitat under here, the little scour pool here is absolutely fantastic. It's that same root wad, the same summer, following summer. As you can see, in terms of habitat, that's really, really good. I know traditionally wood has been viewed as something that is a flood risk and causes big problems. If you can anchor it properly and ensure that it stays there, then it's not. It can be used as a very, very valuable tool. So, in terms of these sort of techniques and solutions, the barriers are the key issues. You can get any revetment, whether it's rock, blockstone, bioengineering, failing because it's not tied in upstream. Very common is undercutting, where the channel in size and cut down underneath, particularly on bends, out of bends. Choosing the wrong species of vegetation in the first place, or establishment technique. Sourcing large wood, that's a constant issue for us, getting enough logs and trees and roots. And these techniques are slightly limited in very, very deep pools. So that's where you need to work with more natural processes to get those pools to fill in. And again, we're always trying to work with engineers to build confidence and reassurance by doing maybe modelling and showing that these techniques will work under certain flows and 1 in 100 year events. But the opportunities are massive. It gives you the opportunity to work with Type 1 materials. If you're cutting down a tree, or it's a tree that's probably falling in, why not reuse it on the same site? Why not reuse it locally? I think there'll be a lot more large wood used to manage rivers stability generally in the future. It's now accepted as best practice or good practice. It does work with local natural processes. It doesn't pass the problems on downstream like hard engineering does. Definitely, fits in really well with natural flood management type works, and obviously enhances biodiversity and all the other WFD and sustainability benefits as well. So, thank you.